Good morning, friends. Welcome back. In today's session, we'll be starting with numericals on strain energy. So, the numericals here are very simple. Better you know that this section is to be attempted in module number 5. It will fetch you more number of marks with a minimal number of time, with a minimum time. Right. So, what I can suggest here is if you are good at integration, you are 80 to 90% done in these kind of problems. Right. So, let us begin with the today's video lecture. I have noted the problem number 1 for you people. Let us go through that. A simply supported beam of span L carries a point load W at the midspan. Find the strain energy stored by the beam. So it is just some kind of a generalized statement given to me. He has not given any values. So no issues. We'll go ahead with this itself. So let me start with the solution. So first thing what I'd be doing here is I'll be drawing a diagram of a simply supported beam. Right. So let me draw a simply supported beam. Okay, so this is a simply supported beam. Please show the supports on either sides. Okay, it ends here. Once again you show the support here at this end. Right, now the length of this simply supported beam, let me take the length, total length as L. So you mark the total length as L. Now mark the load W, point load W exactly at the midspan. So exactly at the midspan you are having this load W which will be acting downwards. Right, so in that case let me mark these distances. Here in this case this will be L by 2 on either sides. This will be L by 2. At another side also it will be L by 2. Why? Because this is exactly at the 50% or the midspan. Next, in order to start with the problem, I need to note down the expression for strain energy stored in a beam. So since this is a beam which is subjected to load exactly at the midspan, we know what is going to happen. The beam is going to sag. Right, it is going to sag like this. नीचे होगा ना, it will be bending like this, it will be sagging like this. So I need to find the bending moment, where the bending moment is present and where it is maximum. We know that at the center the bending moment is maximum in this particular case. So what I'll be doing here is I'll be considering a section. Consider a section at a distance x from the free end. Both are free ends. I'll take it from the left side. Consider a section at a distance x from the left side. Okay, now I have considered this section yy at a distance of x from the left end A. So now bending moment at yy is equal to, so I'll take it as my. So that is force into perpendicular distance. So force here, when you are having this point A and this point B, these are the supports. So there will be a reaction here at A. So it will be reaction at A into the perpendicular distance which is x. Right? I hope you are getting me. जहाँ पे दो supports है and you are having a load which is acting downwards, then what happens? This is going to bend. What you have seen in your simply supported beam. So this bending is supported, or it is assisted by these two things, supports, and these two supports will be given a counter reaction. So that reaction here will be Ra, and in this case it will be Rb. You can just write it here. Here in this case you'll be having Ra. Here in this case you'll be having Rb. Right? So bending moment at section YY is Ra into X. Now here I'll write something which is important. Ra is equal to Rb is equal to W by 2. Why? How did I decide this? Very simple. This is a simply supported beam and the load is at midspan, so the reactions will be equal. This we have already studied in beams. Right? If you are not sure about this, then use the same condition of static equilibrium, that is sigma Fy is equal to 0, and once again you take the moment with respect to this point, then you'll be getting Ra and Rb values. According to me, no need to do that. You directly take it as W by 2 because W is acting at the midspan. Right? So what I'll be getting here is therefore M into My is equal to, this is W by 2 into X. Right? So this you take it as equation number 1. Now strain energy stored by the first half. Now here I'll be doing one thing, because these two halves are exactly equal. I'm calling it as half because this side and this side are equal. So I'll be calculating strain energy stored in this part of the beam, and then I'll be adding an equal amount so that I'll be getting the strain energy for the entire beam. Try to understand what I'm telling. Strain energy up to this point and strain energy up to this point, both are the addition of individual strain energies. Right, what I'm trying to tell is, first I'll be calculating strain energy in this first half. That strain energy will be equal to the strain energy in second half, so I'll multiply the first strain energy by 2. It will be still more clear when I'll be doing that. So let me start. Strain energy stored by the part AC, strain energy stored by the part AC. So I'll take it as AC because I'll take this part at C, this point as C. Right, so first 50% or half the length of the beam, strain energy stored is equal to, it will be the expression for strain energy in case of bending. We have already derived this. It will be m square dx divided by 2ei, m square dx divided by 2ei, and the limits will be 0 to L. But in this case I am considering part AC, so AC is length is 50%, so it is 0 to L by 2. Right, now in this case it is my, so I'll make it as my. Right, so therefore that will be equal to integration of 0 to L by 2, integration of 0 to L by 2. What is my square? It is W by 2 into X the whole square divided by 2 times EI. So what I'll be getting here, so that will be whatever are the common things, or what you can say the constant things, you please keep it out. So here it is, what I'll be getting here is 0 to L by 2. So square W square, next what I'll be into dx, don't forget this into dx, W square into X square divided by, if 2 square is 4, that 4 into this 2 is 8 times EI into dx. Right, so ये मिलेगा हमको. I'll be telling once again, W the whole square is W square, 2 square का हो जाएगा 4, that 4 you multiplied by this 2, it will become 8 EI, X the whole square is X square. Whatever are the constant, you please keep it out. So constants जितने भी है उसे बाहर रख दो. It is W square divided by 8 EI. Now the integration will be 0 to L by 2 X square into dx. Now this is a simple integration. Kindly go ahead and integrate this. Strain, therefore strain energy stored by part AC will be equal to, constants please keep it out, W square divided by 8 EI, this is constant. Integration of X square is X cube divided by 3, and the limits will be 0 to L by 2. So that if I just substitute W square divided by 8 EI, now this is X cube will be L by 2 the whole cube divided by 3. So that will be equal to, कितना हो जाएगा, so 2 cube will be 8, and if it comes down it will be 24. Try to understand, 1 by 2 cube will be 1 by 8, that 1 by 8 into this 3 will be 1 by 24, so 1 by 24 into 1 by 8, so 1 by 24 into 1 by 8, so I guess it is 24 into 8. So it will be W square. This will be L cube divided by 8 3s are 24. Denominator we are having 24. So 2 cube will be 8. This also comes into the denominator. So that is 24 into 8, that is 192. So it is 192 E into I. Right, so this will be the expression for strain energy case of in case of part AC. Now we know that strain energy stored since the beam is simply supported with the load at midspan midspan we have RA is equal to RB, right? RA is equal to RB and both will be equal to W by 2. So this is the first similarity, and also the lengths are equal, that is AC is equal to BC is equal to L by 2, right? Under these two conditions, what I can say, strain energy stored, therefore strain energy stored in AC will be equal to strain energy stored in BC. So this is very important. Right? Why this is equal? Because the reactions are equal, the lengths are equal, and that is the reason strain energy stored will also be equal. Therefore, total total strain energy in the beam, strain energy stored in the beam will be equal to. So you just need to multiply this expression what I got into 2, because both are equal. So it will be 2 into W square L cube divided by 192 EI. So therefore U in this case will be equal to, so let me check out what I'll be getting here. 192 divided by 2, so it will be 96 in the denominator. So it will be W square L cube divided by 96 E into I. Right, so this is the total strain energy that is stored in the beam. Right, so that's it for today's session. Have a great day. Take care. Bye bye.